Hi, I'm Daniel. So we're actually based in Singapore. So last year on January 18th, my kid came. On Llama was released on 15th February, and basically I've just been like holed up coding, rather getting the AI to code for me for the last 1.5 years. Oh my God. Okay. So yeah, and I think we're both actually open source as well as AI. So maybe I'll just do a quick demonstration of what we've built. So a little bit about us. We basically were model trainers. We basically train a bunch of stuff. We basically fine-tune a lot of models, tried training a few foundational models, didn't have enough money. So we started doing a lot of fine-tuning on Hugging Face and all that. That's who we are. We're back-end AI engineers, really focused on the mathematics of it. Everything that we did, nothing grew, except for one. We launched a stable diffusion thing in July last year. It went viral. Actually, a lot of people used it from Taiwan, up until I decided it was a great idea to see what are people like generating, right? So I clicked into the folder and I was like, oh boy, okay, we're gonna get out of this business, right? Because they use it for generating quite interesting things, right? So yeah, but I think after that we started to build a bunch of stuff. So we built then one of the other experiments we built in a local AI thing on the desktop. We built it. Today I think it's about, oh wow, we had 19 stars. Oh, that's more. Okay, we have like 1,000 forks. So I think everybody's like taking it and using it for their own projects and all that. But we're not UI people. We just built the UI to show off what we were doing on the back end. So I actually tried to do a storybook. I couldn't figure it out. And then ChatGPT wrote the rest of the UI, and that's sort of what we've done. How does it work? It's something very simple like this. So you just be like, tell me more about life or something. And this, if I turned off the Wi-Fi, this essentially works on your computer on commodity hardware, and it generates AI. So most people know Ollama. Most people know LM Studio. We're the bootstrapped open source version of I think LM Studio. And I'll share a little bit more about some things that we're doing. So this is what LM Llama 3 8B Q4 thinks about some of this. So yeah, we have some interesting stuff. So I think for us, we're a bunch of open source engineers. Many of them came from me from my previous company. We're just holed up, really fascinated by this technology. But we've actually come out now as the Homebrew Computer Company. That logo is actually not designed by Stable Diffusion. And I think we are, I think, a research institution that's really, really interested in AI, and just building things up and down the stack. Okay, so I think before I bore everybody, I want to just do a rough gauge of where everybody is in terms of your technical knowledge, and then I can scale it up and down depending on how you guys want. How many of you have used OpenAI's API before? Good, wonderful. How many of you have run a local LLM? Wow, this is one of the best, actually. Okay, how many of you have run an LLM in production? Okay, how many of you have built your own computer? This is a very technical group. Built your own server. Damn, you fine-tuned your own model. Trained your own model. Worked with multi-node GPU clusters for inference and fine-tuning. Okay, so I'm going to bring this talk a little bit deeper because I think you guys really understand your stuff, and I think we want to drive on this. What is Jan? Jan is basically a UI that's sort of nice on top of all the other stuff we did. Was it difficult to build a UI? No. Did anybody use our software before I built a UI? No. So after all these years, I've just realized that we've got to learn some React and get with it. Okay, so but I think a bit of the fundamentals, right? How many of you guys understand how a transformer works or the LLM works at a mathematical level? Okay, so for those of you guys, I'm going to keep this talk, I think, a bit higher level, and then later we can go into really the meat and potatoes and the math side. What is an LLM? Basically, the way I think about it is that our human brains are biological neural networks. How the machine does it is a really shitty version, digital version of a neural network. Is it great? Not really. Does it work? Yes. Can it hold a lot of data? Oh, hell yeah, right? And all you need to know for the purposes of this talk is that an LLM basically just, when you use an LLM, the first part encodes it in machine speak. Right, and then it runs through this thing, which is like a neural network. Do you need to understand how it works? Not really. The only thing that you need to know, and then after it runs through the network, it thinks in the same way that our brains think. And once it comes up with its answer, it then gets decoded. in whatever language or vocabulary it is out there. For the purposes of this talk, which is focusing on the machine and the hardware itself, the only thing that you need to know about this neural network is the layers, right? And that'll become important for later. Okay? Another piece of fundamental knowledge, what is in a model, right? When you say I'm running Llama 3, what exactly does it mean? And the reality is that there's so many different versions of Llama 3, right? Because when we're running it and all that, you have Llama, okay, this one's an outdated slide, Mistral 7B, 7 billion is 4 gigabytes, but this Mistral is 24 gigabytes. Why is it so different, right? And the answer is really in terms of the parameters, right? Think about parameters as just really the amount of fidelity, the sort of size of the neural network, right? And the more parameters you have, the better. The other thing is also the quantization, right? And this is, I think, a bit more mathematical. What you need to think is essentially these neural networks operate on like integer and operations and all that, right? So if I asked you, what is 4 times, Brandon, what is 4 times 3? 12, right? And what if say what 4.1621, 4.1621317 multiplied by 3.162171? You say, okay, I got to do a bit of math, but it's going to be around 12, right? Okay, I mean, just so what it is that essentially for quantizations, you have a very large floating point that has to be computed over here. And it is possible to actually reduce the fidelity or you round up in certain versions to make it a bit faster for that computation to happen, right? It makes it a lot faster, but it's still very approximate. It gets roughly there, right? So these are the two important things that you need to know about models. So the bigger thing about all of this is also that these models don't follow a linear curve. When you have these parameters, and okay, I'm making up the human stuff over there. I actually have no idea how many parameters we have, right? But I stole this from the instructed.val GitHub. If you look at over here, MMLU is a reasoning, think of it as an IQ score for machines, right? And what happens is that in the number of parameters that you have, what you see is that, yes, it gets smarter, but it doesn't get smarter like this. It gets smarter like this, right? And that was what was so interesting. If you download Llama 8B today, and it works on your computer right here, and in your system monitor, it is a 4.5 gigabyte file. That makes your computer a thinking machine with almost a full knowledge of humanity available to you on your flight. And this is going to be in your phones before the end of the year. But your phone might get really hot. Okay? So turning back to this, so intuitions again, right? So unsurprisingly, bigger models need more GPUs and hardware, which is why I think I'm here for Computex and why Jensen Huang is making so much money over here, right? And so those of you from the hardware sides, if you just look at this and the amount of VRAM that is needed, it really goes up further and further. And okay, we left out two of these labels. This, I believe, is FP16. This is int4, right? So the quantizations also matter as well. Okay, so, and what does this mean, right? So I'm in Taiwan, so I realize most people here are very familiar with hardware. But what this really means, and when in the Valley and all that, most people have never actually opened the machines, right? And what it really means is that, okay, how many GPUs do you need to run Llama 2 70B, right? For the 3060s, okay, nope, that's not working. Tesla V100s, you need 16. For the A100s, even for that, you need 4 of these guys, right? So these are not simple machines. This is actually what we built Jan on. It was in my room, just heating up the baby and all that. And you have only 7 PCIe slots over here, right? And once you get like to Supermicro and all that, you see, okay, you've got 4 here, the number of PCIe lanes are also there, right? And that really means that AI is really, truly a hardware problem, right? And how do we build software, and more importantly, open source hardware and open source software around these problems? Okay, so my problem was really, I woke up, I was like, oh yeah, Llama's released. All right, let's go run it locally. It basically became this hardware adventure that we've never quite gotten off. And so now, big picture again. In the news, you will hear about teraflops and all that. Teraflops is basically like, how many floating point operations can these machines do, right? And more importantly, what we're finding is that memory bandwidth is really, really important for faster inference. So within that GPU, how fast can the little cores in there talk to each other, right? And why is it important for us as algorithms guys? It's really because all the new algorithms like flash attention, which essentially takes an algorithm which has like 6 or 7 read and writes from state, and you're basically applying linear algebra. You're doing it's essentially all of these techniques are hardware optimization techniques. You're figuring out which things you're keeping in HBM and what you're tossing in the SRAM, right? So it's to that level of detail that the algorithms guys can't just say, okay, my math works, here's my paper, I give you my PhD. We've got to really start thinking about, okay, where exactly are we putting the data? Because that is the difference between a 30-second inference request and something that returns in less than 4 seconds. Sorry, 0.4 and 0.30. No, 0 and 3.0 versus 0.4. Sorry, decimal error. Okay, so again, I'm not sure where everybody is in this. I'll just cover this. So laptops. So this is an overview of computing, right? Laptops, usually they have a GPU. Most of them don't have GPUs. Those that do have it here. Your good friends at Nvidia and all of them manufacture it here. Apple Silicon is interesting. There is no separate GPU. Instead, it's a system on a chip. And they use that unified memory of RAM to basically run all of this. And what is super interesting, last week, Windows announced the Copilot Plus, where essentially, I didn't know, I had to read, I drew this diagram for myself. I'm not sure whether it's correct. So if anyone from Qualcomm, or even know somebody at Qualcomm will help me out. What is super interesting is basically it's this architecture, but they're sort of migrating it over here, the MPUs and all that, right? So it's going to be really, really, really interesting. And this is going to mean like a lot of innovation and almost insane competition, which we're super excited for in the next few years. Okay, desktops, workstations, very, very simple. You basically have a big ass motherboard. You plug, 2 of Jensen's favorite things in there. It might crack your motherboard, it might not, but you just plug it in there. The motherboard is used to communicate between the GPUs unless you have Nvidia's NVLink that links them up in there. Servers, what does it mean? It's basically the same thing, just more expensive. They use better parts so you can run it for 24/7. And it's support, and if you use Intel, there's support for multiple CPUs, right? So this is pretty much an outdated version, the P100s, but you can just think of it as really a computer that is really souped up, right? And what's really interesting is like the multiple servers, so the multi-node computes. This is what ChatGPT and everybody uses to run that inference, right? And so what you have is actually, instead of using a motherboard to let the GPUs talk to each other, these bad boys use like, Ethernet or, InfiniBand to talk to each other. Honestly, I don't understand this stuff. It's not our area of specialization. I'm here to actually go to Computex and try to learn this stuff. So if any of you guys know, I'd really like it. So yeah, and these SuperPod is basically like interact networking. How does it work? I have no idea. I got these diagrams from NVIDIA's documentation. But yeah, so okay. So what is the talk that we're giving here, right? And I want to just explain, I think, something that we've learned, right? So as of this week, I think Jan's been downloaded 1 million times. And the mark of a true bad engineer, we have gotten at least 86,000 crash reports. And that's only when we activated crash reports, like 3 months ago. So we've been very, very consistently failing and disappointing people for the last part of 1.5 years. So yeah, and so we pull stuff from Jan. Increasingly, I'll talk about this later. We're pulling it out into a library. But holy crap, this thing is really in its infancy, right? And we are so early. If you're hearing me talk about this, this is super early. But I'm willing to bet that what we think of as computers 30 years from now will be very, very different, right? They'll be more human-like, and this is really the early days of, I think, how all of this is coming. So I want to explain a lot what we've learned from a lot of those errors in context of like an inference lifecycle request. What does it mean when you ask a computer to think, when you ask ChatGPT to think? What exactly happens at the hardware level and the software level, right? So this is a story of a prompt. Thor, can you give me a prompt? Pretend I'm a machine.
Generate an image.
Oh, no images, just
No
text.
images.
pretty stupid model.
Or do like a chat completion or just like.
No, just pretend I'm a machine. It's not hard.
Okay.
I can do that.
Yeah.
Tell me a joke.
All right. So tell me a joke. And the best, actually, that's live. I feel that's the hello world of AI. Like. Yeah. So what happens? You tell me hello world, and I'm like, all right. So I'm the CPU. I go down to my hard drive. I take out that model, right? 4 gigabytes of it, and I bring it over to the CPU. And over here, and just showing you my diagrams here, this is what the computer looks like. For those of you who have never had it, I met a Gen Z the other day who was just like, wait, laptops? I was like, okay. Yeah. And the Gen Zs like continually surprised me. They didn't know there was like Wi-Fi, there was like Ethernet. I was like, oh my God, nice. Okay, so then you took this stuff and we load it over here. And this is the CPU, this is the GPU. This is sort of our version of the state diagram. So yeah, and all that. So you're loading it from the hard disk to the CPU. And then the CPU and GPU then pushes some of the model layers over into the GPU. And then what happens? And so this one, certain layers are pushed into the GPU. For the rest of this talk, I'm just going to assume that they're putting everything into the GPU. Okay? And then what happens? What happens here? This is very, very important. That memory bandwidth and that speed of memory movement within the GPU as well as the RAM matters because it then gets pushed into the memory of the GPU. And what's so interesting about this is that it's almost like seeing two different computers. You have the traditional computer, which is over here. And then you have, Jensen Land, I think, over here. And that's so interesting on how that happens, right? And then what happens, tell me a joke is run in using a prompt. And what happens is that this one all happens in the GPU, more algorithmic. It gets tokenized into the machine language. And then it gets run through the transformer layers. And all of this is happening right here. Okay? And then the prediction is made. And then it passes it back to the CPU. And usually it's decoded and all that already. To then decode it and pass it back to the user in terms of, so the joke is, actually, I don't have no jokes for you. You gotta ask the LLM for that, right? So this is essentially what's been happening when you push it into the GPU layer. It makes that and it comes out. So that's the easy one. What happens if you have multiple GPUs? Or what happens if you have a model that doesn't fit into one GPU? This is where the math and the hardware come together, right? What happens here? Same thing, the CPU does. It loads its weights and all that, moves it from the hard drive. And then this here is really interesting. It then it distributes some of the layers to GPU 1. It distributes some of the other layers to GPU 2. Remember, it's not the whole thing. And then inference request is run. But here's the thing that is interesting. The way that Llama does it right now, Llama 3, at least to the best of my knowledge from running this thing, is that it actually does it semi-sequentially, right? If you look at linear algebra as aggregative, so it computes some of it on GPU 1, and then it passes it to GPU 2, transforms it over here, and then only after the two of them are done, they come over. There's this sort of function this very, very high level abstraction. It does this sort of operation over all of the inputs that were given that eventually come out over in GPU 2, and then there's the prediction over here. But this is why the communication is so important between the different GPUs. And we've measured it because we run an eGPU and we run like two GPUs plugged into the motherboard. So there's a Thunderbolt cable versus a PCI connection. And the difference is like astonishingly slow, right? And this is so interesting because I think how we build computers is going to have to change if this becomes the primary mode of compute, right? For most of the world's population. Most of us in this room are coders, right? But the vast majority of the world is going to be able to interact with computers and get computers to do stuff by just talking to them. So I think this method and mode of compute will increase a lot in the years ahead. Okay? So now this is the part that I don't know anything about, but I found some good diagrams to show you guys. If anyone wants to step in, please do. I call it my holy moly part of the talk because I have no experience. I don't know how it works. I just read this stuff and I'm like, So what happens? So just a quick refresher, there's the multi-node stuff. And this is basically what NVIDIA's documentation gave me. I'm just giving it to you in full. I have no idea how it works, but just come with me. The CPU, some poor little CPU out there who's like tanking this entire thing on behalf of the entire huge wardrobe of like servers, takes the model weights out of the thing and he says, all right, you get some model weights, you get some model weights, you get some model weights. And it gets distributed across that entire wardrobe of like GPUs, right? And then the part where you hear about NVLink, you hear about InfiniBand and all that. That's the super critical stuff that is about the intermediate communication, where they're sort of exchanging the results, taking the softmax attention, feed forward layers, and passing them between the different GPUs, right? And then finally, some poor guy one of the GPUs in there has to it's a little bit like school homework, I feel, It's like, you're like, all right, you think through this, you think through this, you think through this, and then they pass it back, and then the poor guy, is got to figure out how it all turns out, and then it gives you the final prediction, right? And if you think about it, LLM models are essentially the same across all of the different types of hardware. It's just the sheer scale at which all of them operate at. So again, I have no idea what any of this is, but I just thought I'd put it here. I was hoping someone in the audience could help, but I think, and this is essentially what many of us in town for to learn, I think, about Computex and how does the DGX GH200 work. Okay. Another just very, very quick part of the talk, the LLM inference ecosystem. And we've done a lot of trying to think through and navigate our way around here. Right now, I think one of the most popular things out there is Ollama. Ollama is essentially wrapping llama.cpp. And basically then what happens is that Llama CPP is a cross hardware sort of inference library. It then distributes it to the different computation drivers. Each of the major hardware manufacturers has their own. I'll pass it down to the hardware driver, CPU, and the machines over here. For us, we actually started out, so I think a bit of programming here. I think we started off Llama CPP, built it for TensorRT, LLM for some of our enterprise customers. And now what's really interesting is the Windows Copilot stuff. It runs on this thing called Onyx Runtime, which has always been sort of under-maintained, but it's really, really, really interesting. And we're actually doing our first release of Cortex, the backend library, around Onyx Runtime in probably 2 weeks or so. It's not ready. I'm actually going home tonight to write the README, so just watch it on GitHub. Nvidia's ecosystem, and each of these, essentially the main takeaway that I want you guys to have is really that at the end of the day, when you have these machines, there's really so many different layers of drivers and stuff that are dependent on. But all of it runs down to the same fundamental few things that it's about how do you make mathematical operations on hardware just go faster. Okay, NVIDIA system, quite just giving you guys a high level. Intel also has their own. Right. What's really interesting about Intel's is there's this Windows Direct ML stuff. My prediction over the next 6 months is that space is going to be the most interesting to watch. AMD has its own as well, its own walled gardens here and there. And then Apple is the ultimate walled garden. They just don't have anything other than their own stuff. You've got to just work with all this stuff. But what's really interesting is Apple's unified memory, because it works on your iPhone and it works on your computer. When we first released, we actually released on the iPhone. And this was July last year. And I just kept getting reports of people's phone overheating. And we had to take it down from the App Store after that. Okay. And I think what's really interesting, again, I talked about DirectML. That's the web GPU stuff, WebNN. That's really coming very fast and furious. I don't understand enough about it, but it's really coming very, very, very quickly. Okay, so I think just a little bit about us. I think we're an open source team. Just actually a few people. We used to do model dataset consultancy. We built this. Cortex is the one that I wanted to talk about a little bit. We also do assemble GPU servers and inference machines in Singapore. If you know anyone who wants to buy some, or you want to just play some of this, our cheapest machine is under $2,000, and it runs Llama 7, Llama 8B. Yeah. So, but secondhand GPU. Okay, so what are we doing now? It's really, I think, Cortex. What we really wanted was to build a on-device AI that runs, on any type of hardware. We've built it in C++ because most of the traditional AI libraries are really in C++. It was a holy war fought in my team between Rust, Go, and ultimately it came out as C++. And I think, we've learned certain things from Ollama. It's really very nice. I think what we really want to do was to support multiple engines. Because we think that this space is still growing very rapidly. And, I think for developers, it's really important. Our path as a company is really weird. We built a developer library. We're not in San Fran. Nobody used it. We built a UI. Now everybody doesn't want the UI. So that's life for you. We think that in the future, a lot of this will run on robots. And that's why local AI, if you think of R2D2 or C3PO, I don't think any of them were all right, ChatGPT API key, and he's like, all right, stop shooting me, Darth Vader. Yeah, and I think where we are really trying to bring this is actually as a full open source replacement for OpenAI's platform. Most enterprises today are used to OpenAI's platform. There's function calling, runs, fine tuning as well. We're basically going to build the exact same thing, fully open source. And we believe that the future of AI needs to be open source. It needs to be understandable and auditable. And what we are going to do is to make it so easy for enterprises or anybody to just switch over. Or if you're a small startup, we really love and we came out from this community, and we want to really support that. And my goal is basically to take all the complexity and all the pain that we have felt in the last 1 year crashing on random distros of like Linux to like AVX2 processors from like 2006, right? And it's basically just replaced with this very simple library that we want to use to drive the open source stuff. For us as a team, I think the software sides are honestly a labor of love. We don't get paid for it. We just run it because it's necessary. If you do know people who want to buy AI PCs or GPU servers, that's how we feed the team. Okay, so and last question, I think people always ask, what computer should I buy? And we've done all the perf testing. Actually, today, the best one is the Apple, actually it's not Mac Studio, where I think you get to run, I think, really, really big and awesome models at the cheapest price. Yeah, so I think that's our talk, and hope it take away a lot of the mystique of AI and what you would just realize it's something that runs on a machine. And I feel tinkering with it, playing with it, is really what we want to encourage. So yeah. All right.
I think we have time for some questions.
Yeah.
What do you think about 1-bit LLM?
Sorry?
1-bit.
I heard about it. I don't understand it. I don't know, but we'd love to figure it out, actually. Yeah. The BitNet stuff, is it? The BitNet, yeah. I tried reading the paper. I didn't have time to understand it. If you do, I'd really like to talk. Yeah.
I don't think so.
Oh, no. Yeah.
I'm curious, like, this was a great kind of overview of the whole pipeline. And this is all for the inference side. And then there's the whole training side, which is like a different beast. I'm curious, like, I know nothing. I know a lot about the backgrounds of like machine learning and so on, but very little about the current state of the art. Is the gold rush in the inference side or the training side or both? What's the
gold rush,
relative size of these two different kind of?
It does feel that the gold rush is everywhere.
Everywhere.
But there's a lot of bullshit. I would say the fundamentals have not changed. It's still the same math. It's just like 10 new pieces of vocabulary, and you're just like, hey, you can't. And I just feel like nothing has quite changed. It's just that there's a lot more nomenclature. The same thermal limits, everything's still the same, actually.
But like, would this talk like be easily translatable into kind of
fine tuning,
the training end of it? No.
Oh, it's a completely different deck.
Completely different.
So I think the big thing about LLMs is really so train is very different from vision, right? Vision was actually a very different beast to deal with from LLMs, because the big thing about these LLMs is really that they need to have context of each other, right? And context is basically an n-squared problem, right? Because you're trying to figure out how everything relates to everything else. There's some, and whenever a researcher says n-squared, every PhD is like, yes, I can find my PhD by doing a log n thing. And so there's some optimizations, but I would say that that's not a solved problem.
So I've been following you guys since you were Nitro before
Cortex. Oh dear, that was embarrassing. Oh, thank you.
And at the end of the day, there actually aren't that many players. You're saying it's super early days. The question is, in some ways, Cortex to me feels like it's sharing a lot with Llama CPP. Right?
Yeah.
And what's the differentiation there?
Yeah.
Essentially, that OpenAI kind of equivalent API already existed in some form, right? So what's your vision beyond that?
So I think for a lot of us, we actually are Llama CPP contributors. I think that's how many of us. If you think about Llama CPP, it's basically just implementing it in C++, and then your flash attention and all that comes in. I think where we really see a interesting angle is, I think, really in if you think about Llama, right? There's two parts. There's really the model curation side, that is somewhat interesting, making sure that it's downloadable, it's Docker, of that stuff. On the inference side, now I'm talking as an engineer, not as a business guy, right? And there's a reason why it's free. Engineering-wise, it's not that tough, right? You're just basically writing adapters, and whenever someone breaks something, you're like, you provide first-level customer support. But we do think that there's something quite interesting about this sort of abstraction layer that allows a enterprise or anybody used to OpenAI to switch very easily to open source AI. Otherwise, there's too much friction and all that. And more importantly, if you're used to a singular, I think simple, and I wouldn't say Cortex, I think honestly it's like the OpenAI API, and it being able to run on any type of hardware, and this is going to get tougher and tougher, allows for that sort of these simple frictions. It's a little bit like, we did all this backend engineering, and then the UI is the one that got downloads. And now I'm just like, yeah, you know what? I'm just going to do what works.
I know that you guys had a hardware focus until.
That's how we pay the bills, man. I gotta pay the bills. Yeah. Connor? Oh.
Yeah, kind of continuing on with this question. So from the developer experience point of view, if we're, say we have like a high-end Mac, Apple Silicon, where we've got Llama, which we're using to pull down not just Llama, but Mistral or whatever model. What's the user experience difference between that and your product?
I see. The user difference is really like for Mac, most people will use Llama CPP, right? And for us, I think we've done some optimizations. I think we are anywhere, I think someone posted on Discord or something today. I think we're anywhere between 1/8 to 1/8 to 40 tokens. They do 38, we do 40. So that's speed, right?
I mean the model itself, and I mean just the experience of pulling down the model is like pretty good.
So I think it's very similar. My point of view is that that's actually a commodity. Everyone's going to have that. Where it's really going to pull away from is really when you have to support multiple engines, right? That's not easy, right? And TensorRT, let's just take TensorRT, right? Do you do pipeline parallelism or do you do tensor parallelism?
I just have a subscription to all of Manning, and so I'm going through books and learning stuff. So I'm just playing around with my own machine.
But yeah, even like full Llama and Windows, you have to go through like WSL too. Right? Yeah.
I think.
Yeah. You can't just, they have a Windows preview, but it doesn't use GPU. So yeah.
They do use the GPU. I think they patched that. But I think. Yeah.
But that just goes to your point of like the supporting the different platforms.
Yeah, the more difficult part is really how do you provide that consistent experience across the different things, right? So Llama is really, it's the UX. Why everybody, and I think this is the thing that we learned as backend engineers, it's really the UX, and yeah, like we basically figured this and this out, which are really hard. And then we were just like, okay, so we just need to do like Cortex Pull. Sure, we'll build that, so it's going to come out next week. But like, okay, for like Onyx runtime doesn't have flash attention. That actually has a lot of differences in terms of how that inference is done. TensorRT is where it gets really interesting because Llama right now you can't use multiple GPUs, so it's very, very limited, right? TensorRT will force you to have to dig into the guts of the model, figure out how you want to distribute this between the two layers. Yeah, the two layers. In this case, this is sequential. And maybe brief primer, pipeline parallelism is somewhat more like sequential. Tensor parallelism is where it's really distributed across this. But your algorithm needs to be designed around those principles, right? And yeah, so I think it's going to be a very, very, very interesting area for the next 3 years. Like what we're dealing with right now is just commodity, it's the easy stuff. The pain is yet to come. Yeah. Questions?
Yeah, I'm curious, my understanding from a more software guy's perspective is that a lot of Apple's efficiency really comes from their unified memory. I guess I'm trying to understand, are there products out there that are also building on the ARM platform and utilizing, unified memory, since that really does seem to give you, if you're just working with like, pretty standard hardware, it seems like one of the winning solutions right now. And I'm just curious if there's any other players in the space who are building on ARM using using unified memory.
I'm here to find out. If you want to go to Computex and find out with me, I'd love to go with you. I think the honest answer is that I think, the unified memory stuff is really the correct way to go. At least from all of the stuff that we've done, it's really, I think, the correct way to go about it. So I think that's just sort of where we are. Dude, you've done everything before, so
Yeah, no, the one thing I haven't done is basically train LLMs, but I was wondering, building on the other question, we were talking about having more memory. Is I mean, of course it does, but what is it? Wait, how do I phrase this? For inference, is having a larger virtual, like a GPU memory, more important than having more tensor cores?
oh yeah.
And do tensor cores only come into play when you're starting to train your own models?
So I'm not the expert on that. The high-level understanding that I have, right, is really, or rather, we've been so GPU poor that we never had enough tensor cores to actually see the difference, right? So I gotta be honest here. So if you're asking me like H100, they've got like tensor cores for days. What happens? Well, it goes a lot faster, you know. So I think especially if you look at LLMs, it's very clear. Let me just show you, I think, the breakdown of LLMs, right? That the space is cleaving into two different types of products. You have these sort of 8B, 7B models that can actually do quite reasonably. And they are 4 gigabytes, 6 gigabytes, 8 gigabytes quantized. And yeah, those, you know, fit into a normal GPU and they'll fit into, you know, a phone by the end of the year, right? And then on the other end of the scale, you have these like, okay, we don't even support them, but you know, you have like GPT-4 with like 500 gig model, 600 gig. So that's, you're going to see the space sort of go in two ways, and then you have like different products.
Because when I train some LoRa's for like the models, even though like I was training on I was trying to train on a MacBook, and I was trying to train on like a 3090 from like really old 3090, and it's still faster to train on 3090s than like MacBooks, but inference seems to not be affected by that. So
Yeah, I think inference is a lot easier. Fine tuning is really a different monster altogether, and that's what I'll do a separate slide deck someday to explain. Yeah, it's really fascinating, and I encourage everybody. I think in the open source space, what is awesome is always that you can promote your competitors, and really in the longer term, you're actually colleagues. Download Olama if you're a developer. Download LM Studio if you're a front end guy. Play around with all of those things, right? It's absolutely fascinating that you can run a model that performs the way Llama 8B does, right? Let me just ask it a question about like, tell me more about HBM memory or something. Tell me more about HBM memory for GPUs, right? These guys will just think on your, and they, if you're on a flight or anything, these things are a near human full knowledge of the world as a 4.58 gigabyte file that you can carry with you across borders. I think there's something very profound with that has just shifted beneath our feet.
That seems more than human, no?
I know. I watched a baby grow up. I watched this LLM improve. They are very. This one's Delulu, yeah. All right.
Still, what would you rather have on a flight?
That's a really good one. You got jokes, man. You got jokes. Yeah. All right. Nothing else? All right. How do I disconnect from everything?
Yeah. Actually, on that point, I can